Hey. Hey.
Pretty early today.
Hmm?
It was pretty early.
Yeah, I just gave a midterm in my last class, that's why.
Oh, there we go.
So no one has questions after the midterm. So everyone just went home.
Do you mind if I ask you a question about
Sure.
the project?
Yeah, yeah,
You have
for sure.
some time?
Sure.
I don't technically need this. I think I've had a few questions on, I haven't actually did the historical funds yet. I just been thinking about
Yeah.
process on how I go about it. I wanted to do the,
Okay.
in terms of how I want to apply the application, does that depend on what I use?
Absolutely, yes, yeah, and so that's part of the topic that I want you all to research the part that you're gonna do, and then see, what are some typical moving scenarios for this part.
Okay, so choose an application and then just that application. Obviously, is rejected or whatever it is.
Exactly, yeah.
So I was looking at some, I mean, I've actually.
Nice.
That might be a little bit
Migration, we'll get to that later in this semester, and so I'm not expecting anything like that. And so just the basic like static structure, that's all.
Okay, so are you expecting like, let's say, like, you know how you have varying, right? You have varying housing straps.
Yep.
Do you expect us to like do a little?
If it's appropriate, yeah. I mean, if it's applying torsional load, it's not that difficult. You know, it's just I know we've only done just force and pressure
Right.
loads, but then torsional loads work the same way. You just click on the surface and you apply a torque on that surface.
Okay. Well,
Yeah, so yeah, it's very good. Other people have asked me the same thing. So, yeah, if you think that it's appropriate, then that's definitely.
Yeah, considering how I mean, you're using off of the bearing housing, so like, I was thinking, do I stay away from it? Obviously, I don't want to because I can't. Process, so like, I don't see a shaft being, the number of that is there. Stress. Okay. Is it safe to say that I can do the shaft?
Yeah, I think that's one way to approach it, and there's definitely one way that I was kind of thinking about too. That if, you know, because like I know there's a lot of applications where the shaft is just kind of rotating, it's not
Right,
putting on a force on the bearing, and that was kind of the first thing that I thought of too. If you think that's appropriate, then that's fine. Because then you would just have the two housings on the side. You can apply whatever force you want, torsional or pressure or whatever, and that helps cut down on your number of components too. Because like the main challenge I think this project is going to give is that there's so many components, and so deciding which ones are important for whatever application you're going to do, that's going to be difficult.
Would it be safe to say that you should keep both the housing? Because you essentially have your components.
Yes. Yeah.
So do we need to do the houses on both of those?
That's a good question too. Yeah. So if you think that if it's going to be symmetrical, you can cut it in half.
Unless you have like some kind of over load or something.
Exactly. Yeah.
Or
Yeah.
one of them will see more. I was looking at one of the applications that has like an overhang load.
Yeah.
And obviously the one that's closer to the load.
Right. Right. No, it's a good observation, and symmetry is something that's really important for finding elements too. And you can basically cut your power. And so if you have perfectly symmetrical modes, then you can get away with just doing it. The important thing is that anything that you do suppress or anything that you do cut out of the model, like you have to be able to justify.
Right.
Yeah.
I mean, I'll probably try to get something started. I'll probably probably some more.
Okay. No, I think
As
it's,
we go on here.
yeah. No, I think it's a good start. It's good that you're thinking about it. I think all of these sound really reasonable.
Okay. All right, thank you.
Yep.
All right, it's 5:30, so let's go ahead and get started. Good evening, everyone. How's everyone doing today? Good, good. All right. Okay, so the plan for today is we're going to keep talking about element types. Right? And so today's going to be a little bit of a lightning round because honestly, last class period, I expected to actually get through a little bit more. And so today we're going to be just kind of going through very quickly of all the different kind of element combinations that you can have, right? And so we'll be going over all the different element shapes and all the different element orders, and I'll be drawing each of those elements for you just so that you have an idea of, you know, of how many nodes there are per element and what the cost is per element. Okay, and then hopefully we'll have time to wrap it up at the end to talk about, you know, some trade-offs that you can, you know, that you can think about in general about using the different element types. Okay, so I do want to get through all of this today because on Monday I do want to talk about shell and beam elements because that's going to be really important for the activity we're going to do next Wednesday. Okay. Okay. All right. And so are there? I think that's it for my announcements. Are there any questions I can answer about the project or anything before we get started? Okay. All right. So let's go ahead and get going. And so today is going to be, you know, speed dating with all the different element types that there are. Okay. And so I know we kind of started a little bit last week, but I do kind of want to just start at the top, you know, with the linear quadrilateral again. Okay. Just because I thought about, you know, all that I want to cover, and I want to make sure I get through everything. But I want to make sure I cover everything kind of consistently. All right, so the linear quadrilateral, this is the first 2D element that we're going to look at, okay? And I know most of the analysis that we do in this class is 3D, but even in those situations, you know, your 2D elements are going to be really important. Right? Because for any 3D volume that you're going to mesh, you know, you're going to have a 2D surface on the exterior, right? And so that's going to cover kind of the shell or whatever your 3D surface is, right? And so even if your 3D geometry is meshed with like hexahedrons or tetrahedrons, on the surface of your model, you're going to have the 2D elements. And so, you know, even if you have a 3D situation, the 2D element types are really important. Right? And that's what you look at, right? And so whenever you mesh a 3D object, you know, what you're actually looking at on the exterior are actually the 2D elements. Okay, so for the linear quadrilateral, we have 4 nodes. Okay. I remember what we talked about on Monday about the shape functions, and so this tells us that we have 4 shape functions. And the 4 shape functions tells us that our approximating polynomial or our finite element interpolation polynomial has 4 degrees of freedom, or in other words, 4 different terms in the expression. And so let's go ahead and write out what the what those terms are. Okay. And so I'm going to be using the function t for everything today, and I got a few questions last time about what this t represents. Okay. So what this t represents here is just any kind of generic finite element solution. Okay. And so the reason I use t here is because t stands for temperature. And the reason that we use temperature here is that the heat equation actually is mathematically is a lot easier to solve than structural mechanics equation. And so actually, you know, if we're going through the theory much at all, you know, we'd be actually starting with the heat equation, and that's kind of where these lecture notes came from. And so these lecture notes are a couple years old at this point, and I use them as kind of a sequel to, you know, talking about solving the heat equation in finite elements. And so that's where the t comes from, but you know that t is interchangeable with really anything. And so, you know, if you want to consider this as like a structural mechanics equation, that t would be replaced with deformation, right? Because that's deformation would be the primary solution variable for structural mechanics. Okay, and so our t of x and y is going to be c0, right? And so we always have our constant term in our polynomial. Okay. Then we have c1x, c2y, right? And so these are both the linear terms. Okay. Okay. And then we have c3xy, which is our mixed term. Okay. Right. Now remember, since this is considered our linear quadrilateral, all four of these terms here are considered linear terms. Okay. Even the last one. So even the last one, even though we have a product of x and y, okay, we consider this term as pseudo-linear. Okay. Because it's really just linear in the in each of the individual x and y components. Okay. All right. And so if you remember from Monday, the way that we typically solve for these constants, right? Right, because for any finite element situation, we're interested in solving for the values of those constants. The way that we solve for this is that we enforce the nodal solutions, or the solutions at these nodes, to take on their global values. Okay. And so on Monday, we did this for the 1D case for a 1D linear function. And so, in 2D and 3D, you can do the same thing, but, with 4 constants and 4 unknowns, it starts to get a little bit messy. And so, if we dived into it, then it would take it would be a lot more trouble than it's worth. We'd be spending more time doing algebra than actually learning finite elements, which is, what I don't want. Okay. But by going through that process of solving for those constants, it'll give you the forms of the 4 shape functions. All right. Any questions on any of this? Okay. All right. And so that's the linear quadrilateral. Oh, question?
Can you explain the pseudo-linear again?
Sure. Yeah. So all pseudo-linear means is that we consider it as a linear term, even though technically it's not. And so because we have the product of x and y, technically that's a quadratic term because we have a product of two independent variables. But for x, just by itself, and y by itself, they're both linear. And so we consider this as a pseudo-linear term. And so kind of the requirement for that is that, if we take the derivative, in this case, it'd be a partial derivative of that last term with respect to x, then x goes away. And so that's the reason why we call it pseudo-linear. Yeah. And same thing with y. Yep. Okay. All right, so that's the linear quadrilateral. And so now let's go over the quadratic quadrilateral. Okay, which again is a 2D element type, right? All right. And so to get our quadratic quadrilateral, we're going to start with our linear quadrilateral just like we did before, except now we're going to add some additional nodes at the midpoints of the edges. Okay. Right, and so what I have in black right there, those are the normal nodes for our linear quadrilateral. But for our quadratic one, we're going to add these nodes here on the mid sides. Okay. Okay. And so overall, by making the transition from linear to quadratic, what we have now is 8 nodes. Okay. And remember, each node represents, the number of nodes here represent the number of shape functions. And so we're going to have 8 shape functions. and also eight terms in our polynomial. Okay. All right, and so let me go ahead and write out what the finite element polynomial is for the quadratic quadrilateral. And so we have t of xy is equal to, okay, and so we have 8 terms here. And so we have c0 plus c1x plus c2y plus c3xy. Okay. And so those are all the linear terms, and so we still maintain each of those terms. Okay. And then from here we start to add our quadratic terms, because we have 4 more to go, because we have 8 nodes, and so we need eight terms here. Okay. First thing I'm going to write is the individual quadratic terms. So we have c4 x squared plus c5 y squared. Okay. And so both of those are quadratic, because if you take the derivative of those terms with respect to that variable, and so we take the derivative of c4 x squared, and we take the partial derivative with respect to x, then that term still maintains an x value. Okay. Right. We need 4 more terms, and so we also are going to have c6 x squared y plus c7 y squared x, and those are our 8 terms. Okay. And so again, with this guy, we see c6 and c7, even though technically, the overall power of those terms is cubic, because we have, x squared multiplied by y, and so the overall power of that is 3, which is, cubic. But individually for x and y, we have only quadratic terms. Okay. And so, we again have to rely on these pseudo terms to kind of, make it work with this many nodes. Okay. Okay. And so you can see that, by making the jump from linear to quadratic, we have a pretty significant increase in the cost, right? And so, whereas for the linear quadrilateral, we had 4 nodes, this one we have 8. And so it's an increase of 2x, right? And so we basically double our cost per node, we double our cost because of this. Okay. And just because these mid nodes here in red, just because they're not on the corners of our element, it doesn't mean that they don't have the same requirements, right? Because remember, the requirements for the nodes is that the finite elements solution should be consistent across those nodes, right? And so if we go from, one element to the next, and so let's say that we have a neighboring element here, right? Kind of going beyond that, okay? These 2 elements share this node right here, right? And so the solution should be consistent at that node. And so what that means that, we shouldn't jump from one element to the other one and have the solution be one thing in one element and then the solution be something different at the other one. Okay. So all of these nodal solutions should be consistent throughout the entire mesh. Okay. Okay. Any questions on this? Okay. All right. So one other thing I want to highlight about this element compared to the linear one is going to be all the quadratic terms, right? Okay. I guess I did need to circle them because they were already in different colors, but it's okay. All right. And so the main benefit that we get from these quadratic terms is that we get non-constant strain and non-constant stress. Okay. Right. And this is really important because what this tells us is that when we compute the strain field or the strain solution on this element, we're going to get a non-constant value, right? Because remember, the way that we compute strain is we take the derivative of our solution function with respect to space, right? And so in this case, we take the derivative with respect to x, and then we take the derivative with respect to y, okay? And because we have these four terms right here, that tells us that, even after we take the derivative, we can have strain that varies across the, across the element, because we'll still maintain, these terms, right? And so if we look at the C4 term as an example, right? And so we take the derivative of the C4 term with respect to x, we get 2C4x, right? And so we still have that x term in there. And so what that tells us is that there's still ways for the strain to vary within that element, right? And that's really important when you're doing structural mechanics, because then you avoid that shear locking phenomenon that we talked about before. Okay? Right. And so if you remember, we talked about shear locking a little bit briefly from before, but shear locking is the phenomenon that, that can happen when you do structural finite elements with linear elements. And that's a phenomenon where the stress in your element tends to be constant. And so when you have a constant stress element, then you end up with just deformations that are much lower than what they actually are. Okay. But I will say that, for quadrilaterals, it's actually not that bad, because, if you look back at our equation for our linear quadrilateral, okay, we have this pseudo-linear term right here, okay? And so even when you take the derivative of this, you still get some variation, right? And so if you take the derivative of the C3 term with respect to x, even though x will go away there, y is still present. And so, there is room to have some variation of strain within your linear quadrilateral, and so it's not as bad. You can still get a pretty reasonable solution with with linear quadrilaterals, for structural mechanics. And you'll see that same principle applies for 3D as well. So for the hexes, you still get some variation, and that's why I've kind of been saying up to this point that if you can mesh with either hexahedrons or quadrilaterals, you generally end up with a little bit of higher quality solution if you use linear elements. And so, if you can swing it, then quadrilaterals and hexes are preferred, mostly because they have these pseudo-linear terms. But again, it's not a necessity. And so I've talked to several people in this class, where I think they've tried to do the activity on their home laptops, and then they just haven't been able to produce a hex mesh on anything that we tried. And it's okay, and if you don't get it, it's fine, because again, you're using quadratic elements. And so with quadratic elements, you really don't have to worry about shear locking at all, whether you're using triangles or quadrilaterals. But if you are using linear elements, try to use the box type elements if you can. Okay. All right, any questions on this? Okay. All right, so those are the quadrilaterals. So now let's start to look at the triangles. Right, and so this is going to be the linear triangle, and so again, this is a 2D element. Okay, and so the linear triangle here, we have three nodes. Right, so one node less than the quadrilateral. Okay, and this tells us we're going to have three shape functions. Okay. And this tells us that we're going to have three terms in our polynomial. All right, so let's go ahead and write out what those terms are. All right, so with three terms, it's a lot simpler than than the quadrilateral. Okay. And so we just have C0 plus C1x plus C2y. Okay. Right. And so in the triangles case, we have something that's just purely linear. So we don't have any pseudo terms at all. Right. So no weird arguments that we have to make about whether this is a linear function or not. Okay. And so mathematically, this is actually really convenient. And actually, for kind of I call it kind of the partner class for this class 541. Where the final project for that class is I have everyone basically implement their own finite element code in MATLAB. I have them do it with triangles, and it's actually a lot simpler than if I had them do it with quadrilaterals. Okay? Mostly because it is purely linear. All right, and so mathematically, this is a lot simpler, but it also comes with its disadvantages as well. Okay, and so because we don't have that mixed term or that pseudo-linear term, okay, then this means that if we take the derivative of this function in any direction, whether x or y, we're going to end up with a purely constant. Okay. And that's bad for cases or for equations that rely on their derivatives, specifically like the structural mechanics equations. Okay. And so this is the point where ANSYS will actually give you a warning. And so if you're doing like a static structural simulation and you choose to use linear triangles for it, ANSYS will tell you that this is not a good idea, and you should either try to produce a hexahedral mesh or a quadrilateral mesh, or you should upgrade to quadratic. Okay. All right, any questions on this? Okay. All right, so that's the linear triangle. And so the next our next guess is going to be the quadratic triangle. Okay, where again, this is a 2D element. And just like we did with the quadrilateral, we're going to start with our linear triangle. Okay. And then we're going to add some additional mid nodes. Okay. And so on the middles of basically all the edges, we're going to add additional nodes there. And so overall, we have 6 nodes. Okay. Which is going to give us 6 shape functions. Which is going to give us 6 terms in our polynomial. All right, so let's go ahead and write out what that polynomial is. Okay. And so we have t of xy is going to be equal to c0 plus c1x plus c2y, right? And so those are all our linear terms. And then we have our quadratic terms from this. And so we have plus c3 x squared plus c4 xy plus c5 y squared. Okay. All right, and so 2 less terms than our quadrilateral, our quadratic quadrilateral, but we still get our our non-linear terms here. Okay. And so because we have this person, and this person, okay, what these will allow us to do is that when we take derivatives of this quantity, they can be non-constant across the element. And so if you have a particularly challenging geometry, you know, where you can't put a hexahedral mesh on it, or you can't put a quadrilateral mesh on it, then you can use a quadratic triangle or a quadratic tetrahedron, you know, and you're still going to be okay. Yeah, question.
How come we consider the mixed term here quadratic, quadrilateral? Just to serve the purposes that we need for that particular shape.
Yeah, it's a good question. And so technically, you know, this term is still pseudo-linear, but pseudo-linear is also still quadratic as well. And so it's, you know, the how we choose these terms, I think, is based off, I think it's called Pascal's triangle. And so you start out with kind of a linear term up top, and then you kind of build the terms kind of like that. And so, you know, you can kind of think of it as, you know, the more nodes that we add, we kind of bring in some additional terms off the bench. And then these are kind of the first terms that are off the bench, you know, once we get up to a quadratic. Yeah. Mhm. All right, any questions on this? Okay, and so let me go ahead and move on to the 3D elements, and then we'll come back to this stuff if we have time. Okay, because I do have a little bit more notes on shear locking, but I think at this point, you know, we've kind of talked about it enough. You know, basically the ideas with shear locking is that, you know, you want to use quadratic elements for structural mechanics, and that'll take care of all your shear locking problems. Okay, so now let's move on to the 3D elements. And the first on the list is the linear tetrahedron. All right. And so remember, our tetrahedron here is our four-sided pyramid. And so the way I usually draw is something like this, okay, where the two nodes on the sides are connected in the back by a dotted line. Okay. Right, and so you can see here we have four nodes, which is going to tell us we have four shape functions. Which means we have four terms in our polynomial. Okay. But keep in mind now we're in 3D, and so now we have the z direction that we have to deal with as well. Okay. All right, and so our approximating polynomial looks like the following. So we have c0 plus c1x plus c2y plus c3z. Okay. And so just like its triangular cousin in 2D, you can see that all of the terms here are purely linear. Okay. And so there's no pseudo terms here at all. And so no matter which direction that you take a derivative in, whether it be x or y or z, you're going to end up with a constant term. Okay. And so the linear tetrahedron here, because it has so few nodes, this is really the simplest 3D element that you can have. Okay. And so if you're implementing a finite element code for the first time, so you're coding up your own, and you want to do a 3D simulation, then linear tetrahedra is where you're going to start, just because it is so simple. And then you kind of add more complexity on top of this. Okay. All right, any questions on this? Okay. All right, and so that's the linear tetrahedron. And so now let's go to the quadratic version. Okay. And so just like we've been doing for our quadratic elements, we're going to take our element shape, and then we're going to put additional nodes on the middle of each of the edges. Okay. Okay. Right, and so if you count the pink dots on there, you'll see that there are 6 additional nodes. Okay, because we have 6 edges in a tetrahedron, and so overall this is going to give us 10 nodes. Okay, 10 nodes, which gives us 10 shape functions. Okay. Which is going to give us 10 terms in our polynomial. Right, so let's go ahead and write out what those terms look like. Right, and so t of x, y, and z is going to be equal to, first we have all of our linear terms from our linear tetrahedron. Okay, and so we have C0 plus C1x plus C2y plus C3z. Okay. Now we have all our quadratic terms, and so we have C4x squared plus C5y squared plus C6z squared plus now we have our mixed terms, since we have C7xy plus C8xz plus C9yz. And so we have a big jump here. Okay. And so we went from 4 nodes in the linear version up to 10 nodes in the quadratic one. And so I want to kind of draw your attention to a trend, okay? And so for the 2D triangle, okay, so for the 2D triangle, we had 3 nodes in the element, and for the quadratic one, we have 6, right? And so going from here to here is a 2x increase in cost, okay? Or a 2x increase in the number of nodes. Okay. Whereas for the 3D case, you know, our linear version had 4 nodes, and then our quadratic one had 10. Okay. And so you can see here, this is a 2.5x increase in the cost. Okay. And this trend is consistent between the quadrilaterals, right? And so the linear and the quadratic one, and you'll see very soon for the hexahedra too. Okay. And so what this means is that in higher dimensions in 3D, you pay a little bit more of a cost to go from linear to quadratic. Okay. Fortunately, my iPad, I can't write in that bottom corner. But basically what that says down there is you pay more cost going from linear to quadratic in 3D. Okay. Relatively speaking. Okay. It's not, it's, you know, I think someone asked a question on Monday. It's not that, you know, you're always going to get a 2.5x increase in the amount of nodes, because remember, nodes are shared between different elements. But you can expect a, you know, higher, you know, a big proportional increase in that sense. Okay. Okay, any questions on this? Oh, question.
If you were to make a cubic tetrahedron, would you just add additional nodes in between each of those quadratic nodes?
Yeah, that's a good question. You would start to actually add nodes in the interior of the element as well. And so those are unique because those any interior nodes are not shared between different elements, because those are just within that element itself. But you're gonna have to do that just to make sure that you have enough terms to cover everything. Okay. So actually, the first thing you would do is you would add nodes in the middles of the faces. Actually, that would be the first thing that you do. And so you would have 4 more nodes in the middle of each of those faces. But that only gives you 4 more nodes. And so then you would, and then, to accommodate all the cubic terms, you would add more in the middle of the element. Yeah, it starts to get pretty nasty once you get to cubic. And so, practically speaking, there oftentimes there's not that much reason to go beyond quadratic. But if you are working with an equation that's like, I think electromagnetism is one such equation where you have like 4th order derivatives, then those are cases when, going up to that, it makes sense. Yeah. All right. Any other questions on this? Okay. All right. And so now let's talk about the brick elements. And remember, the other name for a hexahedron oftentimes is a brick because it looks like a brick. Okay. Okay. And so the brick looks something like this. Right. And so if you're like me, Amazon drops off one of these in front of our door once a week. Okay. And so with this, you can see that we have 8 nodes here. Right. 8 nodes means we have 8 shape functions. Okay. Which means we have 8 terms in our polynomial. All right. And so let's go ahead and start writing these out. All right, and so our function here, t of x, y, and z, we have our linear term, c0 plus c1x plus c2y plus c3z. Okay. Then we have all of our pseudo terms, and so all our cross terms. Okay, and so we have c4xy plus c5xz plus c6yz. Okay, and we actually need one more. And so technically, this is kind of stretching a little bit, but we need one more term here because we have the 8th node. Okay. And so the 8th term here is actually a cubic term, but it's a pseudo-linear term. And so we have c7xyz. Right. And so once again, even though we have a linear, technically this element type is linear, you have all of these cross terms here, right? So all of these kind of pseudo-linear terms, where if you take the derivative of this function or of this element, in either direction, you can still have some variation. Okay. And that feature, the fact that you can still have some variation after the derivative, helps prevent shear locking. Okay, and so so even if you do end up using linear hexahedron for your for structural simulation, it's still not ideal, but it's also not that bad because you're still going to get some variation in there. Yeah. But honestly, if I had to choose, between a linear hexahedron versus a quadratic tet, I'm going to go with the quadratic tet most of the time because the tetrahedron also still has some nice properties associated with it too, and then you never have to worry about shear locking in that case as well, right? And so in most cases, I don't think that you would be in a situation where you would use linear hexes versus like a quadratic, either a quadratic hex or a quadratic tetrahedron. But in the case where you do find yourself in that situation where maybe you're in one of those fringe cases where you're trying to save cost as much as possible, then you're going to be okay. But there's not that many situations where you would be stuck in that situation. Okay, so any questions on this? Okay, all right. And so the last element type that we're going to go over is the quadratic hexahedra. Okay. And so, if we follow our trend from before, and so remember when we looked at the linear versus the quadratic tetrahedron, there's a 2.5 increase in the number of nodes, okay? And so that's true here too, right? And so if our linear hexahedra had 8 nodes, then if we multiply that by 2.5, that means that our quadratic version is going to have 20 nodes, right? And so it's always quite an experience to draw. Of course, it's a lot harder here on the iPad than it is on the board, but I'll try my best. Right, and so in my notes right here, I call these elements the kind of the Rolls Royce of finite elements, and so this is kind of the best that you can do. Okay. So I made some other connections in there. So I call them, what else? This is like the filet mignon or the Louis Vuitton or the Whole Foods of finite elements. Okay. And so it's really expensive, but oftentimes you're happy with your purchase most of the time. Okay, and so there's all the linear nodes, right? So those are going to be at all the corners, and so now we're going to add all the nodes in the middles of the edges. Right? So node here, node here, node here, node here, here, here. Here. There should be 20. We can count them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, got them all. Okay, so we have 20 nodes, right? And so that means 20 shape functions. Okay, and that means there's going to be 20 polynomial terms as well. Okay. All right, and so we're going to write out all 20 of these terms. All right, so let's start. Okay, so we have all of our linear terms first. We have C0 plus C1x plus C2y plus C3z plus C4xy plus C5xz plus C6yz plus C7 x, y, z. Okay? And so those are all the linear terms that we inherited from the linear hexahedra. Okay. And now we're going to add all of the quadratic terms. We have C8 x squared plus C9 y squared plus C10 z squared. Okay. Plus C11 x squared y plus C12 x squared z plus C13 y squared x plus C14 y squared z plus C15 z squared x plus C16 z squared y. Okay. And then we have the cross triple terms. Okay. And so we have C17 C17 x squared yz plus C18 xy squared z plus C19 xy z squared. And that's all of them. Okay. All right. So quite a doozy there. So a lot of terms. Okay. And so every polynomial term that's technically quadratic under the sun, is here. Okay. A lot of these terms are like, they're pseudo quadratic, but they look like fourth order terms because they have four terms multiplied by each other, right? And so whenever I see, some of these last terms here, like the C17 term, C18, C19, right? These guys are, trying to pretend like they're quadratic. So they're like, I always imagine the memes like, how do you do, fellow quadratic terms? And, but they actually have four terms associated with them. So, but there's a lot. And so, it's a lot of terms and a lot of, polynomial orders. But this is good. And so this is kind of why these elements here are so preferred, because basically every single way that a function can vary in x and y and z, with various powers of x, y, and z, all different combinations are here. And so, whatever, weird kind of behavior that your finite element solution might have, even if your finite element solution is not a quadratic function, maybe it's something cubic, I would say you're much more likely to capture that behavior because there's so many terms in this, in this polynomial here. Yeah. And so that's why, when you can swing it, and if you're able to do it from your from ANSYS, and you can use a quadratic hexahedron, then this is the one I think that gives people most confidence in your results. Okay, just because there's just so many different variations that you can do here. But whether all of these are really relevant or really important for capturing solution behavior, of course it depends on the boundary conditions and the specific situation. But this kind of gives you the most flexibility and kind of the most the biggest amount of solution kind of variability that you can have. Okay. All right. Any questions on the quadratic hexahedron? Okay. All right. All right. And so the next thing I want to do, so now that we've seen all the different element types and all their glory and what their polynomial function looks like, I do want to talk a bit about how do you choose which element to use for a specific application. And so I want to talk about where certain elements are good, where certain elements are bad, when you want to use linear and quadratic and so on and so forth. Okay, because that's really the practical decision that you all are going to be making when you use your finite elements, right? On the one hand, it's fun to see all the polynomials that comprise these elements. Or at least maybe for me, because I'm a big nerd, but I think what most people are interested in is, well, how do we actually use these in practice? All right. Okay. And so the way I'm going to break this up is I'm going to make a table, okay? And I'm going to list out kind of the pros and cons of each combination from this table, okay? And so I'm going to group. I'm going to do a little bit of grouping, and so I'm going to group the triangles and tetrahedrons together in the same category because they have basically the same properties. And then the quadrilaterals and the hexahedrons, I'm going to combine them together too. Okay, and so you can almost think of them as like the 2D and 3D versions of the same thing. Okay. Right. And then in one column, I'm going to have the linear behavior. Okay. And in the other column, I'm going to have the quadratic behavior. Okay. This one is a little bit more excited. Draw a little bit to the left. Okay. All right. And so what are some pros and some cons for the triangular element types, for the triangles and tets? Okay. And so one of the biggest benefits and kind of the biggest reason why you would choose triangles or tets is that they can be used to mesh any geometry. Okay. Okay. And this goes for both the linear and the quadratic versions. Okay. And so that's why I kind of overmapped it into both. Okay. Right. And so this is a huge plus for this because no matter what kind of crazy geometry you throw at it, triangles and tetrahedrons will mesh it without any errors. Okay. And so that's a really big benefit. So whenever you have kind of a new or complex geometry and you're not sure where to start with the meshing, I always tell people to start with a tetrahedron or start with a triangular mesh because you know that you're gonna get a mesh on it, right? Maybe it's not the best quality mesh, but it'll at least get you past that meshing step so that you can start applying boundary conditions and you can actually start to run simulations. And so, maybe the tetrahedron or the triangle might not be part of your final solution, but it will at least be a big key part of the process because it'll help you debug, it'll help you test some things, and it'll help you see how the solution looks like beforehand. Okay. And so this property right here, the fact that you can use it to mesh any geometry, this is called the simplex property. Okay. And so basically, all that basically means is that triangles and tetrahedrons, they can form any kind of simplex that can fill any space. Okay. All right. And so one downside to this is that even though they can be used to mesh any geometry, they're not that efficient in doing so. Okay. Okay. And so what I mean by that is that, even though you can use these triangular elements to fill any space, it's going to take them quite a few elements to do that because they have this kind of lopsided, shape to them. Okay. And so, if you end up going with the tetrahedral mesh for your project or something, and you start to refine the mesh, what you'll see is that the number of elements is going to jump up quite a bit. Sometimes up to the point where you can't even run it on specific versions. Question?
So is it safe to say the skewness of your mesh has a higher probability of increasing if you're using tetrahedrons or triangles?
Oh, yeah, it's a good question. I would say there's less probability actually with the triangles and tetrahedron because because they have this kind of strange shape and they can be used to fill any geometry. They actually don't need to contort themselves all too much to fill space.
Okay, so they don't skew as
Yeah,
much.
they're less likely to skew. But that doesn't mean that they can't skew, and so they still do. But compared to the quadrilaterals and the hexes, I'd say those are more likely to skew themselves. Yeah. Mhm. All right. And so another downside to specifically linear triangles and linear tetrahedron for structural simulations is that you have shear locking. Right? Remember, shear locking is that phenomenon where if you run a structural simulation and shear locking is present, then you're going to end up with very underestimated deformations because literally all of your elements are going to lock up and not deform as much as they should. Okay? And so, in other words, it adds a lot of artificial stiffness to your structure. Okay? And remember, the main reason behind that is that if you take the derivative of your linear triangle or linear tetrahedron, you end up with a purely constant number. And so that means that each of your elements is going to be constant stress, which leads to locking up. Okay? Whereas if you use a quadratic tetrahedron, then you don't have to worry, or a quadratic tetrahedron, quadratic triangle, you don't have to worry about shear locking. Okay? Because you take the derivative of a quadratic element, you're going to still get something that can vary across the element. Okay, which is really important for structural equations, which rely on the gradients of stresses in order to determine what the deformations are going to be. Okay. All right. And so what are these good for? Okay. And so for linear tetrahedrons and linear triangles, these are usually great for thermal simulations and for fluids. Okay. And so this is typically where you'll see them the most. And so for quadratic tetrahedron, these are great for fluids and thermal, but also for structures. Okay. And those are usually the main three areas where people run finite element simulations for. And so they're usually running a heat transfer simulation or a fluid simulation or a structural simulation. There are others that exist, mainly for, I would say, for chemists and for electrical engineers. And so you can do like chemical reactions and electromagnetism. And I will admit that I don't really know or have any experience with that to really comment on it. But if I had to guess, I would say at least quadratic for those as well. Because one thing I do know about reacting flows, about chemical reactions, is that there can be very high gradients. And so things can change, over the course of, of millimeters, even less, if you're talking about like a combustion reaction and things like that. And so, any situation where you have high gradients, quadratic is going to perform a lot better just because you have those non-constant terms, after you take the derivatives, right? And even without taking the derivatives, a quadratic term is going to be able to vary a lot faster and have, much sharper gradients compared to a linear term. And so that would be my guess, but I don't want to comment on it too much just because I don't have all the experience. Okay. And so now let's go over the quadrilaterals and hexahedra. And so these are in the same category. Okay. All right. And so the plus side to this is that when you can get them to work, they are very efficient at filling space. Okay. And so if you compare, right, if you compare, you mesh the exact same geometry with the exact same element size, and you compare your mesh with tetrahedral elements versus hexahedral ones, then you're gonna notice that the hexahedral mesh does it in less elements compared to the tetrahedral ones, just because they're better at filling space. Okay. The downside to hexahedron, and many of you have experienced this already, is that they don't always work. Okay. Sometimes you'll try to put a hexahedral mesh on something, and then ANSYS will just give you an error message. Okay. And 99% of the time, it's not a particularly helpful error message, and so it'll just say that I can't mesh this, and then it'll just quit and then go home. And so, not the most helpful, but it is what it is. And the reason behind this is that because hexahedra and quadrilaterals don't have that simplex property, researchers are still working on algorithms on how to develop, a really efficient hexahedral meshes. Okay? And so actually the one that you're using in ANSYS right now, the algorithm that ANSYS uses to fill a space with hexahedron, it's very much a proprietary thing of ANSYS. And so that's not something they share with other people. Because I'll tell you, from the other side, I did a little bit of development on finite element code myself. It was really difficult to find, open source packages that does a hexahedral mesh. And so, we're using it in ANSYS as if it's something that's, that's just kind of standard, but it is kind of something really special that ANSYS has that, not a lot of codes don't actually have. And so most codes actually they use tetrahedron just because they just don't have the capabilities to mesh hexahedron as well. Yeah. All right. Okay. All right. And so one benefit for the quadratic one is that just like its tetrahedral counterpart, you don't have to worry about shear locking. Okay. And then for the linear version, I would say it's less of a concern, but still not ideal. Okay. And so I'll give this a meh face. Okay. And so, it definitely wouldn't be as bad as the linear tetrahedral, but it's still, it's still a concern because you don't have all the quadratic terms that the quadratic element has. Okay. All right. And so what are these good for? And so, just like its triangular counterpart, the linear version of this is going to be great for thermal and fluids. Whereas the quadratic one is going to be good for thermal fluids and structures. Okay. All right. One thing I forgot to mention in terms of the fact that hexahedrons don't always work is that they particularly struggle to mesh curved geometries. And so your hexahedra are going to work really well for I would say I call it kind of blocky geometries. And so geometries that have a lot of straight edges, have a lot of sharp corners, right? Because that's what a brick looks like. And so, but if your geometry has a lot of smooth curves, then that's what it's going to struggle with, right? And I think a lot of y'all experienced this with the last two activities. And so with the bike crank, the bike crank, it was relatively blocky, but it still had some curves to it. And so I saw that there were quite a few computers that really struggled to make the hex mesh on it. And then with the last activity too, with the cylindrical post, I noticed that some struggled to do that as well. Okay. And so if you can't put a hex mesh on something, it's not the end of the world. So don't stress about it too much. But it is better if you can. Okay. All right. Any questions on this? Okay. All right. And so let's go back to that topic of hex meshing a bit more. Okay. And so one tip that I can give you, if you really want to get a hex mesh onto something, is that generally it becomes a lot easier when you refine the elements. And so if you're trying to produce a hexahedral mesh on a geometry and it's not working, it's giving you an error message, try refining the elements, try making them smaller. And so sometimes this will help you out quite a bit, okay? Because the main reason why hexahedral meshes fail on certain geometries is that as the mesher is trying to fill a space with elements, it'll sometimes reach a part of the geometry where there's like kind of a really awkward space that's left to be filled, okay? But if you have a big kind of chunky, big hexahedral element, then sometimes it's just impossible to fit that in. Okay, but if you have smaller elements, then it makes it a lot easier for all these little gaps and all these little awkward spaces to be filled. Okay? Because in theory, if you refine the elements enough, you should be able to put a hexahedral mesh on almost any geometry, right? And so in the extreme case, you can refine your elements to basically be the size of sand, right? And so you can fill any container with sand, right? And so in theory, you can make it small enough to fit. But then again, this is speaking from someone who has no idea how a hexahedral meshing algorithm works. And so there might be other reasons why you're not able to do that, even with the really refined element size. Because I've certainly seen cases, with my own testing and with students coming to ask me, where it's just for some reason ANSYS just thinks it's impossible to put a hex mesh on a geometry, no matter how small we fit the elements. But generally, if you do make the elements smaller, it'll make it easier to fill that space. All right, and so 5 more minutes. Okay, let me just go over mixed meshing one more time, because I want to make sure that we go over that. Okay, I know we've already experienced mixed meshing on the last activity, but I think it's useful to kind of write it down in the lecture notes as well. Okay, And so what mixed meshing refers to is, using different meshing settings for different parts of the geometry. Okay. Right, and so you all have already done this in activity 3, right, where you have you apply different element sizing and element methods for both the post and the sum, right? Because both of those geometries, they look very different from each other, right? And so one, we have a very long cylindrical post, okay, and in the other one we have a basically a rectangular sum, right? And so that's perfectly okay, because a lot of times, you're going to want to apply certain shapes to one part of the geometry and certain shapes and certain orders to another part. Okay. And, the ultimate goal that you should have, when you're doing mixed meshing is that, by applying, the most fitting element settings for certain parts of the geometry, you're going to get the most accurate solution while reducing the cost as much as possible. Okay. And of course, this extends beyond, element orders and element shapes as well, right? And so, just like we talked about in activity 3, that, this mostly applies to the mesh sizing, right? And so in the areas where you expect to see, the highest stress concentrations or the highest solution gradients, that's where you're going to want to pack in most of your element density. But for the parts of your geometry where you expect, maybe not that much interesting is going to happen, and you don't really care what happens over there, but you need to include it to apply the boundary conditions, you can probably afford to coarsen the mesh in those areas just to make it more efficient for the things that you're looking for. Okay. And that's an important consideration for your projects as well, right? And so, as you're starting your projects, think about where are the areas in this geometry, based on the loading that I'm going to apply, where are the areas in this geometry where I expect the most interesting behavior to happen, and then let me pack as many elements as I can in those areas. We're trying to, while trying to lessen the costs in other areas. Okay. All right. Any final questions before we wrap up for the week? Okay, right. So that's all I got planned for today. So thank you all for coming. And so next week, we're going to be covering actually 2 new element types. And so we're going to be covering shell and beam elements, okay? Because that's going to be a precursor to our activity 4, which is going to be on Wednesday, right? So have a great weekend, everyone. Hope you guys have a good evening, and I'll see you guys next week. Hey. Yeah, that was for 4 times. Okay. Yeah. So I wrote these notes. These notes are actually a couple. Yeah. So I wrote these notes a couple years ago, but the content is still good. But obviously we're not taking it.
Okay, yeah, because I was like, can I not read this syllabus?
There's no.
Yeah. I was like, wait a second. Thanks for that.
Yeah, no problem.
I have one question. When
Sure.
you said
Yeah.
they don't go down the searches, right?
Yeah.
So this is the issue with the answers or every CUT? So
Pretty much everything that I've seen. Yeah.
like,
and
you know,
so-
sim scale.
I would say so too. Although the only CFD software that I have experience with that can do hexahedrons is just ANSYS. And so I don't have that much experience with other softwares. But I always imagine that the struggles are still the same because with hexahedra, at least from all the papers that I've read, they really struggle with those curved surfaces because they're so blocky. And so in order for them to fit those curved surfaces, they kind of have to bend a little bit themselves, which they normally don't like to do.
One more question. When the last assignment of the signpost.
Yeah.
When I was doing the simulation, when I chose the mesh as the quadrilateral. So why the emphasis like the mixed and mesh?
Wait a second.
So I chose the quadrilateral, right?
Yeah, yeah.
So, but then after the mesh, message pop up that there are still triangle elements in this.
Yeah.
Why? Because but I have already chose that.
Yeah. So for those, sometimes it's impossible to put hexahedrons and quadrilaterals on everything. And so that's why the name of the setting is hexagon. And so ANSYS will try to put as many hexahedral as possible. But then for some cases where it can't, then it'll switch to triangles for those cases. And another thing too is that if you added any refinement, and so the refinement object, the refinement doesn't work with the hexahedron. So if you use any refinement, it's automatically going to convert.
Refinement. So from the first activity, so in the tutorial, so we chose a refinement tree.
Yes.
Yeah.
So like when should we use 1, 2, or 3?
Yeah. So all that number refers to is how much smaller the elements are going to be. And so roughly you can think about it as that for each level of refinement, so level 1, level 2, level 3, then the element sizes are going to be that times smaller compared to the global size. And so refinement level 3 means it's going to be about 3 times smaller than what the global size is.
Or for example, like if our global size is 2 millimeter,
Yeah.
then it will be 3 times more smaller.
Exactly. Yeah. So it'd be two-thirds millimeter.
Thank you so much.
Yeah. No problem. Yep. Have a good weekend.
I don't really want to lift right now. I don't really want to lift.
Yeah.
weights. I kind of just want to do my cardio and go home. But I'm probably just gonna do a modified version of my normal workout. Like, cause I just do all my whole upper body 3 times a week.
Dude, that's what I should be doing.
Yeah.
But like, yeah, that's what I normally do is two lower days, 3 upper days. That's how I would normally train. Obviously,
Yeah.
I think. And my hips all Good news is though, I have been doing. that
So
Side glute.
so if you don't
Bunch of abs and stuff. It's like that's where.
Good girl, bad girl shit?
Yeah, that's what I call it. Bad girls, yeah.
So-
Whenever I say good girl, bad girl machine, nobody knows what the fuck I'm talking about. Like,
Really? What else
how
do
you
you
ever
call
heard that?
What else?
Because they know
They
that-
call it the sus machine.
Oh, the
Shut
sus
up.
machine.
Those Gen Z.
Oh, dude.
Yeah,
You see a guy with the phone busted out here and go there.
So it looks like it's kind of
Yeah.
choosing.
So I've been doing that shit and it's really been helping my hip out
So you
actually.
see
Because, like
actually-
it's getting your pelvis like back where it should be. Like you're not my abs, my glutes are getting stronger. Because like I don't have access to it.
Especially the-
My gym in LA, it's like
Because they're so.
it's like the power.
Right.
So like they have machines, but they're very limited in what they have. So
And same thing for the
yeah,
shaft.
it's pretty nice, but like I just want to get back to being able to train my legs, but dude, I don't even know how I would
And you
maintain.
can kind of see it's an schedule now.
I'm part of the hanging on to
If you don't watch it, you see that.
Yeah.
I think what it's doing there is.
Yeah, look at me talking about my top beach trains.
I got it one day last week.
All week.
That's the best.
I mean, dude, at the very, you could hit like one full body workout, like some squat, bench, deadlift, the accessories type shit.
Right.
But like, you're really just gonna be like either maintaining or like maybe even slightly losing
Yeah,
on
yeah,
that,
for
but
sure,
you're
right?
losing a little bit less than you would doing nothing.
Yeah, exactly.
But I
Looks like
mean,
it
you know,
kinda
you could still keep a
shows-
significant amount of muscle just doing one hard as fuck full body. So it is what it is, but yeah, I just don't, I couldn't fit anything into my schedule like this at all whatsoever. It just-
And you
Especially
kinda
when-
have to,
especially
oh,
when
so you
just
just
want
wanna-
to on top of all that, like, yeah.
Oh, okay, you can just suppress everything else, so.
I mean, you might be able
Because
to do like,
if it's part of this active window residence.
Well, it's just,
then it takes
what I have
effect
to do is
part of
fucking
the
do
analysis. So even though you
that's
don't
dog
do
shit
it,
that
Yeah.
you lose sleep.
Later on, you have to wake up at 5, it gets into the 6, and be at work at 8, and that's how you can do it.
So if you just want to look at the mesh.
But I'm studying
you need to suppress everything.
Yeah, no, that's dog shit. I mean, you could realistically, you could do one day during the
Yeah,
week,
because if you,
Saturday, Sunday,
right now, you
3,
don't have any mesh size.
you know, 3 full body days, and then,
Tuesday-
or
if
like
I-
one full body day, then Saturday
gonna get
upper,
installed.
Sunday lower, some shit, like some
Later on.
split like that.
Yeah.
That's pretty probably the best you're gonna get.
I'm good with my
So that's how you
schedule, and
know.
I do this fucking
You can-
homework
you can
like
see it.
throughout the week, and I could definitely go
So
Tuesday, Thursday, before
Everything, shit.
5:76. I get up at 4:30, and I'm like, hey, if I can lift, and I can make
So if
stuff,
you just want to look at the mesh for this part.
But I'm always like, oh no,
That's
I
the
gotta.
7.
Alright, so-
Yeah.
But I'm always like, oh no, I gotta fucking gotta finish that homework.
Yeah.
Like even tomorrow, I'm gonna be like, bro, I need to finish that homework.
Yeah, I mean, you could probably do Thursday, Saturday, Sunday. You could probably do a split like